All right, so this is class 17, packet 5, Monday after break. We'll deal with 2D quantum bomb today, conservation of momentum. Let's see what's going on. That was the week before break. Now, most of you taken that have taken the test, which I emailed. I should have emailed it to you, the 150-point test 5A. This one right here, if you haven't, you can stick around at the end of this, and we need to make arrangements for you to take that, because I've graded all the in-person students' tests, but I've got to open up all of yours. This is not going to be fun, but I've got to open up all of your tests tonight through email. You either print them off, but then I mean, I mark them all up, but then what am I going to do? Email them back to you? That's crazy. So probably just, you submitted them, which is good. I'll probably just have to grade it and just say stuff like, okay, on number 1, you got a 7 out of 10 or something. And then I can't really tell you why. So anyway, one of the problems of virtual. I think when I teach virtual for real, starting in a couple of years, you're gonna have to have an iPad. I don't know what else to do it. But so I'll grade yours tonight, and probably take me a couple of nights. It's kind of a slow process with yours, and those grades will go in tomorrow night. So if you haven't taken it, you still take it now. You lose some points for being late, but you're not gonna get a 0. And then let's keep going here. So that's last week. Then this week, fairly uneventful week, except that my grades for the semester go in tomorrow night by midnight. So I'll put them in, I don't know, sometime tomorrow evening. So anything that you've not turned in, you probably, if you want it to go on your grade, you probably need to do that like real quick. Submit it or email it to me, whatever it is. Look for 0s. Blanks are nothing. They don't hurt you, but 0s do. And then the only thing that's going to be on there that isn't on there right now, that'll be the test. But looking at grading the in-person students test 5A, I'm talking about, that was the one where it came from the practice problems. Well, some students didn't do the practice problems, and it showed. If you didn't do the practice problems, that test was a bit of a nightmare. And so there's some pretty low grades for some students, but I mean, some of you got like a 156 out of 150s. I mean, so people blew the top off the test, and others are sitting at a 20 out of 150, you know? So it's a wide range. Anyway, that grade will go in the grades, because I have to, I mean, you know, for your parents, I got to show you what's going on. But I realize that's not fair in a way to you, because there's no blue or black. Well, there's no black on these 150-point tests. I've made that decision, only blue. There's no blue points. So, you know, it's a raw score going in there. And so what I'm going to do is I'll take the cushion, which is now 77 out of 77. I'll bump it up to 100 out of 100. That'll help a little bit more. Anyway, so that'll go in tomorrow night. And then on Wednesday is flex day for us, for the in-person students. And that'll be for when we meet Wednesday, we'll do a blue day on the test. Now, you probably have your test, right? Because you emailed it to me. Some of you turned it in, like Sophia, a couple of you turned it in. But to be honest with you, I don't think they need a lot of blue points, so they're probably fine. The two, Eric and Sophia, turned it in, but they're not going to need blue points, if you know what I mean. So if you want to do blue on that, you can still do it, fix it on yours, and then resubmit it. Resubmit it? How's that going to work? Or email it. Anyway, we'll figure that out Wednesday. And then I'll put that grade in, and you have, Friday, you have till Friday to turn that in. You'd either do it, turn to my porch. You probably would do it through Canvas Submit, okay? I guess there's a 4th choice, and that's just to email it to me. Email me a PDF of it. That's another choice, I suppose. But I prefer Canvas Submit. So I'll change that submission date to later, so you're not get like weirdly counted late or something for it. But oh, no. It's worth 0 points. So is Elizabeth in here? Like last time she got confused on that. But this one is worth 0 points. If you don't turn it in, it's not going to hurt you. I tried something on packet 4B that I made it. Anyway, that's a different deal. So anyway, you'll turn it in, you'll submit it by midnight Friday. It's probably what most of you guys will do. And then I'll just give you the points, the blue points. There's no reason to turn that into the porch, really, just submit it. So that's this week. Questions on that before we go to look at the next 2 weeks after that? Questions on this week? We're going to meet every day. Yeah. Wednesday, flex day for us doesn't matter. It's still 1:10 to 2 o'clock. May not take us that long. Okay. And then look for your grades. If you look at your grade tonight, go, whoa, then let's get it fixed, because tomorrow night it becomes, quote, official. Now, I had a lot of parent conferences. Some of your parents texted me, or we Zoomed. If they missed that and they want to do it, that's still fine. They can stick around at the end of this and jump on there at the end, or they can set up a Zoom time with me. Okay, so that's this week, fairly uneventful. And then then it starts to heat up again. Next week is the end of March, believe it or not. But next week is the pre-week to test week. So you have your 150-point test, your take-home test 5B will come out on Monday night. I'll hand it out to them but you'll have it available, a PDF of it on Monday night, a week from tonight. And then there's a remote learning day on Wednesday. I don't know how that'll affect you. I don't think it will. I think you're just cruising right along. I don't know. How do you guys, if you're juniors, aren't you supposed to take the state tests? Like science and history? That's what they're given on Wednesday. Don't you have to take the state tests?
We were able to sign up to do it next year if we want to.
Oh, okay. I mean, could you just say, I'm not going to do it? That's probably what I'd do. Unless you think you're going to blow it away or something. Anyway, so that's next week. We'll worry about that next week. Believe it or not, it's no fooling. It's April 1st on Thursday. It's crazy to me that we're already almost up to April. And then the week after, that's test week. So for you all, it's slightly different. Their test is the 8th. Your test will be like we do normally on these big tests. Your test will be available on the 9th. That's their feast and film, which you're welcome to come by if you want. If you've had a shot or you want to double up your masks or something, and you can certainly come join us for our feast and film. It's a fun day. Pick first, second, or third hour, and bring a little food with you and hang out with us. So we watch this Einstein thing. It's our last feast and film of the year. So it's a lot of food, and you'll stuff yourself. That's on the 9th. But we will not meet that day. I'm talking way in the future now, but that's the day you will get your test. And then I'll put in I got to add in the virtual kids instructions here, but you'll turn it in on the 10th like we do by 6 p.m. Okay, so that's what's coming next few weeks. And let's see what else we got here. One more thing I wanted to show you. Maybe. Oh, I'm got the wrong screen. Okay. I got this from Ollie Bridge. He said he was having trouble with Facebook, but then I talked to my students. They opened up the laptop right there in class, and they got on Facebook. So I think it was just his. Just don't worry about it. Here's the new review sheet. Not review sheet, new help sheet. Side 11 now is available. And it's the thing, it's mostly on momentum. In fact, it's all about momentum. There is, of course, the momentum equation we're dealing with right now. It seems simple, but there's some difficulties with it. And then there's the 4 equations, which is really just one equation with modifications, recoil, those kind of things. I've been dealing with those for a couple of weeks. I also included the kinetic energy, which, just because that's the way it was, when I teach kinetic energy, we'll come back and link it up to conservation of momentum. And then there's the 3 conservation laws of physics mechanics. That's what we study. We study mechanics, and then even AP physics just studies mechanics. That's all that you're required to know. Most high schools don't go to E&M. We do a third year. We didn't do it this year because of COVID, but we do a third year, and that's E&M. But that's sort of a little bit on your own. That's what we've been doing the last couple of weeks is conservation of momentum. That's one of the main pillars. These are like the 3 pillars of mechanics. Conservation of energy, that's of course the basis of everything we do. You can't get more energy out of a system than you put in. But we haven't talked much about energy. We'll talk about forces starting at the end of this week, and then we talk about free body diagrams all next week. Hopefully we're there. And then we talk about work and then energy after that. So we'll get into conservation of energy. We'll dominate the rest of the year once we get to it and all the ramifications of that. And then there's conservation of angular momentum, and that's something that you really don't hit until AP physics. The reason is it requires calculus to understand what's this thing's called moment of inertia. I could throw a bunch of equations at you, but to understand it, you have to have calculus. And so just the broad qualitative definition, like when a skater is wanting to, a skater goes into their spin, they want to speed up, right? They bring their arms in and they spin faster. And that's basically conservation of angular momentum. The rotational inertia is conserved. And so if you change the radius, the thing speeds up to conserve angular momentum. So it's kind of cool that the physics of an ice skater is the same as the physics of a neutron star. When a star collapses, it rotates faster. So like our sun rotates, our Earth rotates, our sun rotates. Most heavenly bodies rotate unless they're, tidally locked or something. But our sun rotates as well. And if our sun's not going to do this, our sun isn't big enough. It needs to be 1.4 times its mass for it to turn into a neutron star eventually. But larger mass stars will collapse in on themselves. It's a process that was first discovered by Jocelyn Bell in 1966. And we finally understand it now. But when stars collapse, they rotate much faster. In fact, neutron stars will rotate once a minute. Like, can you imagine if a day on Earth lasted 1 minute? Sunrise, sunset, sunrise, sunset. But actually, much faster than that. Neutron stars spin once a second. And these are stars that are much bigger than our sun. And they're rotating once a second. Got you beat. Some rotate once every half a second, or once every 15 milliseconds, they rotate. So they're going around like 100 times a second. And it's insane. It's insane. But we actually have all this evidence. We know they're out there. But that's conservation of angular momentum is what drives that process. So the same thing that drives a skater rotating, also it's the same physics that drives a star imploding. And then the last 2 things on the sheet are what we're going to do today, which is 2D collision problems using head-to-tail method. It's like head-to-tail method on steroids. Hopefully you understand so far what we've done because it's about to get harder. But this shows things colliding and how you determine the resulting vectors of collisions. Okay, so that's there for you to look at. Notice that the ghosts are in green. I do my ghosts in green. I do my resultant in red. I see I didn't do it there that way, but oh well, that's the way I do it now. This is an old key. Okay, so that's the new stuff. Today we didn't do a dyno hunt because there was nothing that was due. I've now added this little thing. What about virtual? And so things there's nothing for you as well today that's due to keep up. We'll do something tonight. We'll have a homework assignment. Did our joke Monday, a little Mitch Hedberg, and then today's physics. So by the way, so you guys miss out on all these joke Mondays and stuff, and all the stuff we do in class, going to the board, doing activities, doing demos. And if you, like I say, if you have a shot, if you've had a shot or your parents have had shots and people at home seem cool with it, then I would love for you to switch and join us in person. Some of you are very comfortable, I get it, at home. Some need to stay at home for various reasons. But if you just want to come up for physics, I would probably choose third hour if I were you. Second hour is too crowded. First hour is fine, but man, they are quiet in there. Maybe I could use a little bit of you guys in the first hour. So I'd pick first or third hour. But third hour, you get more of a polished presentation. I've done it twice, and it's a little smoother. So third, plus it's right by lunch. You can stick around afterwards if you had a question. I stayed till 12:25, so you'd have like 20 minutes there to talk to me about a problem you're having. So if you're struggling virtually, you might consider coming up to Norman High at 11 a.m. And I'll treat it any way you want. If you want to just not even tell attendants you're there, and that way you make a choice. Bennett was doing this last semester. He hadn't recently, but he would come up when he felt like he needed to. And I would love to see you guys and have you guys in the classroom, even if it's once a week. So think about it. Coming up about 11 a.m. and stay until noon. Then that way you can blow off you can blow this thing off. You don't have to come to this thing. So up to you. I understand COVID concerns and all. Okay, anything about all that stuff that needs to be talked about before we go on to today's physics? Good. Okay. All right, so I guess we'll keep going. All right, so what we're going to talk about today is conservation of momentum. That's all week. We'll start to move away from that to the F equals ma and all that stuff, to free body diagrams. But we're going to work on this. But it gets harder this week, no doubt about it. This is about as hard as it got for one-dimensional. You'll see one or two of these on the take-home test next week, where you have to put these things together. But now we're going to talk about the actual vectors and things hitting, not like it's a contrived situation, two trains hit and collide. I mean, come on. Something's on an air track. That's not real life. Real life is things hit at an angle and they glance off each other or they stick together. So then you have to deal with momentum, the momentum vector. Well, it's different than a velocity vector. Most vectors we've dealt with are force or velocity. Force is a suitcase as well, but we don't really break it up very often. Momentum, you have to break it up. So momentum, if that's a momentum vector, we know that, and this will probably go in your notes, or you can just write hey, by the way, on notes, for packet 4, you got a lot of notes out of those practice problems, right? But here, we'll include the practice problem sheet, but it's not going to be included in your notes. So you're not going to get all those credits because you've already gotten points for you. You should have points in the grade book for those. You submitted them, and I gave you points for them. So that means that your notes for packet 5 is 75 points worth have got to come from what you're writing down. So if you haven't started any notes, I would start right now. You got a couple of weeks to get some notes on the paper. You probably need to get the full 75 points, you probably need about 5 or 6 pages of notes. So I'm not saying you can't do practice problems. You can go ahead and do a whole page on the Mars rover if you want, whatever you find interesting. I love those kind of things. So anyway, this is probably a good thing to have in your notes. So this is little p, and little p is mass times velocity. So hidden in here, in that orange arrow, there is hidden mass. What's the mass? I don't know. It's like a Trojan horse. Also hidden in here is the velocity. Hidden velocity. So like this could be a lineman on a football team walking because he has so much mass, he doesn't need to walk very fast to have a big, long momentum arrow. It could be a ballerina running, not much mass, but running fast. So I don't know what the arrow is. So you have to, you'll see what I mean. You have to do a little extra work at the end to pull out that hidden mass or to pull out that hidden velocity, because it is what we call a suitcase vector. Okay, that's a Norman High original, so probably won't see it in a textbook, but a suitcase vector means that there are more than one thing in there. It's not just velocity or just force. Okay, so this is what we're working on today. We're mostly going to work together. We're going to go through number 1, and then I'm going to give you 2 and 3 for homework. But I'm not going to leave you hanging. There's a help video for each one of these. So in the comment section, there'll be a slide on help video to help you on each one of these. But let's do number 1 together, and that way you can ask questions or in the comments or in the chat, or you can stop me and ask what the heck I'm doing. All right, so you'll need, unfortunately for this one, I think you're going to prefer this method to what we'll do tomorrow. Tomorrow we're going to do full out component method, which is nasty. One of the nastiest things we do all semester. And we'll do that tomorrow. But for today, let's do it head to tail, which is more visual and actually easier. Now, what you'll need, though, is a ruler. You need really a protractor. You might be able to wing it without one, but it's a little harder. So a protractor with metrics on it, or a protractor and a ruler with metrics. You can get these things at the dollar store for probably 50 cents, but you really need to have one. I pass them out in class, but all right. So now also you'll need for these problems, you'll need 3 colors. One for the regular, don't do pen. Don't use a pen. Oh my goodness. No, it'd be a mess. Because you end up erasing a bunch and you're constructing these things. Now constructing, when it says constructing, it means use a ruler and a protractor. Like we're going to draw an arrow here. I don't want to see, this kind of stuff. There's my arrow. No. Okay. This is like a blueprint. Okay. It's my dad was a civil engineer, and as a kid, I would go, he would help me how to draw and all. And he'd be very precise. So this is pretty precise stuff. So none of that slop, no shaky freehand stuff. Okay, so the first one, we have to draw this. It says using this scale, here's the scale, 1 centimeter equals 100 kilogram meter per second, which is weird. That's a weird unit, but that's mass times velocity. So typical scale, 1 centimeter equals that. We start off with momentum A. It's 20 kilograms. It's moving at 30 meters a second. So 20 times 30, it's 600 kilogram meter per second, which translates into 6 centimeters. Now mine is a different scale than yours, but I kind of know where it goes. So now you get a ruler out, and it says it's moving due east. Okay. So let me draw this thing. It's about that long. Here's where your half arrows come in, half heads, arrowheads. If you do a full arrowhead, the problem, I don't like, maybe it's OCD, but I don't like when arrowheads overlap because you need that space to measure and to write things in. Okay, so this is low P A I. You could say A naught if you want, but like with velocity, this is all historical stuff. So with velocity, they say V naught, they say X naught, right? They say A naught for kinematics. But for momentum, I guess it came along later, they say I as the initial, F for final. Okay. So here's object A moving along. It's let's say it's a lump of clay. I know it's contrived. A lump of clay on a ice skating rink. So it's pretty heavy. I mean, that's about 50 pounds or 45, 46 pounds. Moving along at 30 meters a second, pretty fast. So that's a big arrow, a lot of momentum. And it's going to hit, and inelastic means a stick. It's going to hit object B, which is 10 kilograms at 40 meters. So that's 400 kilograms, which is 4 centimeters. Okay, so and at 30 degrees north of east. So I'll get this little, and some of you have iPads, you can probably find a program that does this, but this has a little ruler on it and it measures my angle. So this is 30 degrees, which is about like that. I say about, I mean, yeah, that is 30 degrees exactly, but let me get the length right. I only know the length as I've done this a number of times. I'd have to measure with a ruler if I didn't. Move that up a little bit. They're supposed to collide where that little star is. Okay. Boom. And now I'm going to do my other half arrow. Get out of there. Okay. See the two half arrows. So now that little space in here is not overlapping. Okay. You got to have some style. PBI. Trust me. You think do not discount, do not poo-poo the idea of being careful and being clear in your writing. Like Ella Sexton, of all my students, a lot of you are very good at how you show it, lay it out. She lays it out really well, and I guarantee she gets. I was talking to her mom about it. She probably does get more points on a test, partial credit, because I know what the heck she's right. I know where she's at. I know where her head's at. I don't know if Matt Houston. He's a nice, but he's really brilliant. But he's all over the place. It's like I can't follow his logic, but he gets it right most of the time, so it doesn't matter. I know you guys. Sarah's really good. Sophia. I mean, a lot of you guys, and I mean, Brandon, give me a break. I mean, the guy's got everything's color coded. It's just amazing. And Rose, look at a lot of you guys are, Eric, you guys are very thorough, Io. I mean, so I'm preaching to the choir here, but having it neat makes a big difference. Well, okay, so that's them coming together, they stick, and this is like in a police, like if a car wreck, say two cars hit and their bumpers lock up and they both slide off as one. Now I realize parts go flying, but let's say that it's mostly contained. A cop comes along and he has that little wheel, he's measuring skid marks on the pavement and stuff. They're basically using law of conservation of momentum, 2D collisions to determine your momentum vectors. They know the weight of the car or the mass of the car. They take that out. Now they know who was speeding and who was breaking the law. So they have little formulas they follow. So that's what we're doing here. We have these two coming together, and then they're gonna stick. Now since they're sticking, and I don't have my props here, but I have these wooden arrows I show. So they're sticking together. So the resultant is simply adding the two vectors up. So let's go ahead and just add those two up. This is as easy. I hate to tell you this, but this is the easiest problem you're going to get on this stuff. Do a little line of action. Line of action. It's just a guide. But line of action, you go as far as you want it to go in both directions. And it's just a visual aid. That's all it is. There's really it does not have any, well, it's important because now I'm going to redo this. Now I want to go head to tail. We've done this a number of times. We've been doing this for months. I'm going to slide B. I could slide A, but I'm going to slide B and hold it now. Here's your you need another color. I'm going to use green. From now on, the rest of the semester, green will be the color I'm going to use for ghosts. Ghost is another Norman High original. My student teacher from about 7 or 8 years ago started saying ghost. I like that, so I use it now. She teaches physics up in Seattle. She still uses ghosts. That's her, and it's kind of neat because it's telling you these aren't real. These are ghosts in a different color. And I don't know why it does that. Okay, so I'm redoing B. I'm just drawing its ghost. 30 degrees, okay. Same length, whoops. Ghost. About there. You do it exactly. Okay, do a half arrow, and that's PBI again, it's ghost. Now I just do head to tail. So now the resultant goes to the very beginning, the very end. So here's my resultant. This is mathematical resultant, which we're trying to see what the combo is going to do. Okay, And I'll do the other half arrow. That's my resultant, an R, mathematical. If you left it like this, you're about halfway done. You get a 5 out of 10. For the 5 out of 10. I got to draw. That's not, I'm trying to show, say it's a police report, I'm trying to show where this combination started from. Well, it didn't start from back here. It started from the collision. So now I got to redraw R and draw the actual combination momentum vector. So here we go. I'm just gonna, and all I'm doing is repeating it. You could draw a line of action if you want to help your eyes, but that's a pretty long arrow. So I'm gonna repeat this. Get the length right. 1, 2, 3, 4, 5, 8, 9, 10. Okay. And this now, hold it. This is no longer a ghost. This is for real, but it's the resultant. So I'm going to make it red. I'm going to make my resultants red the rest of the year. About that. So that's just R repeated. And now this is P, little p final, little p A plus B final. Okay. Okay, now you get a 6 out of 10, probably a 7 out of 10 on a test if you left it like that, because you have to describe it. And the description is not easy. First off, we got to get the angle. We already have that. Let's go ahead and figure out the angle. I'm getting about 12 degrees. I'm going to go 12 degrees. So I'll blow this up a little bit. So in my description, I need 4 things. I need mass, velocity, angle, quadrant. Okay. So in general, let's write that down. In general, you need mass, units, of course, with units, mass at velocity, at angle, and then quadrant, angle in the quadrant. Okay, so I already know it's 12 degrees, so I'm going to put, I'm just talking. You guys can certainly stop me anytime. Erase that. Okay. At 12 degrees, let's see, at 12 degrees north of east. Remember, all your angles are from the horizontal or the east-west line if it's map viewed. And then the mass is easy, right? Because they combined Lavoisier, conservation of mass. So 20 plus 10, we have 30 kilograms. Not a bit lost, not a drop. 30 kilograms at, and then at. So now right in here, we need the velocity. Okay, you tell me, how are we going to get the velocity? It's hidden.
Would you take the slope of the 2 first vectors, maybe?
You don't need slope here. It's simpler than that.
Would you just take the average of the velocities?
Nope. Because these are all good ideas, but the thing is, angles really determine, like, you're going to get a portion of that velocity. It's weird, I know, but you don't take the average. It's simpler than that even.
Don't you measure and then divide by 30 and use the scale? That's
it. So there's a 2 points for that. 2 points for the Facebook points. I mean, Zoom points. Some of you forgot to put your Zoom points in, so I added Zoom points in, like, because I know a lot of you helped and you just forgot to, or you on your packet 4, you forgot to include it, so I just stuck them in there for you, what I thought they were. Anyway, so yeah, so you take the length, use your scale, and when you do that, you get about 10 centimeters, right? That's about 10 centimeters long. That's what we're getting in class, which is the same thing as 1,000 kilograms meter per second, right? Because it's 10 to 1. So 1,000 kilograms, that guy right there, I don't need that anymore. Let's get rid of that. that guy right there is 1,000 kilogram dot meter per second, because that's the scale. So I pull out, like, I just divide that by 30. So 1,000 divided by 30 is 10 divided by 3, which is about 3.3, right? So that's 2 siggies, the best we're going to hope for on head to tail. So that's 3.3 meters per second. That's a hard thing for students. It really is. I get it. I get it. It's tough. It's tough to kind of think through all that. These are all like vector representations of what's really happening, but that's how the police do it. And then the cop goes, "Aha, you were speed." Well, this is a combination, but what they would do is they would have the red arrow, and then they would have to go back and reconstruct the blue arrows. That's a different ball game. We'll get to that later. But anyway, that's it. Solved.
Mr. Askey,
Yeah.
wouldn't the velocity be 33
No.
points?
Two. That's automatic 2 zoom points. What the? I did it 3 times correctly today, and then I do it here and I do it wrong. 33, 30. I think 33, 32. We're getting. Is that right? Yeah, because it's 1,000. Okay. So then the cop says, "Oh well, they're working their way backwards." All right, so 33 meters a second. So yeah. Okay, now I hate to tell you this part. You're not gonna like this part. That was the easiest problem you could possibly do. On 2D collisions, that is the easiest problem you could possibly. Now I know it's your first time you've done it, so you're going, "What's going on?" But that is the easiest. Now 2 and 3 are a little harder. 2 is the second easiest kind, and then 3 is pretty much full on. You got to do it. So this is homework time. We have a little bit of time to work on it. We're going to work on it in class, on here. Like we worked on it in class a little bit. This is going to be, this right here is collision 2. Okay, I know it doesn't seem right. That's collision 2. Otherwise, you'll go off the page on 3. This is collision 3 right there. Okay. Okay. Hold on. Stop. So now let me show you this. Let me share. Stop this sharing. Let me show you. Okay. Here we go. Nope. Okay. Let me show you this. Easy wrong. I showed them. Okay. Google Chrome. Okay. Maybe, yeah. Okay, here's I have, and I'll let you see this tonight, and I'll put these links up. Here's number 1 we just did. So I have 3 solid on help videos. I used to put bumper music on these. I put at the beginning and the end. I put bumper. Then YouTube got me for copyright. So now it's all silent. But anyway, it's a silent help video. This is what we just got finished doing. If I went too fast, you could either rewind and watch the recording of this, or you could just watch this. So there's that one. That's for number 1. And then also I'll put these links up. There's number 2, which is homework. And for them, they're getting 3 stamps if they do 2 and 3. 2 and 3 are homework. And then there's number 3. So these are all worked out. That's a 2-minute, 45-second help video. But what I would do is I would work on it. If I were you, I would start working on number 2 and then go, whoa, I'll get to the point where you're going, I don't know what to do now. We'll start in a second. But then just go back and don't just sit and watch the help video. I mean, work it, then you work it some, then go, okay, now what do you do? Then go try it. Go back and forth, I think is the best approach. Well, we got about 7 minutes. Let's start number 2 together. And number 2 is different because, well, okay, let's just start it. So 2 says that 25 kilogram object A is moving 22 meters per second due north. It has an elastic collision with a static, keyword there, static 5 kilogram object B. So big object coming in, hitting a little object. B then moves at 40 meters a second. So it tells you what happens to B at the end. And then the question is, what was A? What happens to A after, what happened to A after collision? And believe it or not, I mean, things do follow law of conservation of momentum. They really will do what you think they're going to do. So that's what they do with like IUDs. If they come in, say somebody has an explosive device and it blows up and it sends shrapnel here and there. They go back and you'll see the police little flags they put in, and then they start putting lines and they go back and they reconstruct, how much muzzle velocity was from this and what kind of bomb was it. All those kind of things come from conservation of momentum, 2D or 3D. In that case, it's even more complicated. All right, so 25 times 22 gives me 550. So that's going to be 5.5 centimeters. So this, when you draw A, that's going to be 5.5 centimeters due north. So we're on this one down here.
Mr. Askey.
Yes. Oh,
Your
sorry.
screen is-
You're right. My bad. Keep forgetting I'm sharing the wrong screen. Thank you, IO guy. That's always a zoom point for catching me on something. There. Okay, so on this one now, and we're at go back to this. So we're drawing A. It's 25 kilograms, moving at 22 meters per second. 25 times 22 is 550. Due north. So 550 is 5.5. Oh, geez, sorry. 5.5 centimeters long, which goes to about the bottom of the page up, or the bottom of that graph. 5.5. We'll go blue. And boom. Boom. All right. And then B, okay, so that's little PA. Oh, I got 5 minutes. Okay. So that's little PA AI. But B is just a dot. Now it wasn't it's a glancing blow. If it hits it straight on, B's going to go. It's kind of like if you play pool. If you're a pool player, this helps. So that helps a lot. I play a lot of pool, or I did. Grew up with a pool table. So always playing pool. So always looking at the angles, right? And if you think about it, in a pool game, you have 15 balls in a triangle, racked. And then here comes the cue ball. And so the just before collision would be one arrow, like this blue arrow here. And then just after collision, it will turn into 16 arrows. And that's 16, two-dimensional. And that's what a good pool player does. They start looking at the angles. What's going to happen after I hit? Where's the cue ball going to go? Where's the, and that has something more to it because it has English, right? Spin. But you want left spin, right spin, down spin. But that's a different deal. But at least it gives you in the ballpark. So that's your setup on this one. Then after the collision, it says that B then moves 40 meters a second at 50 degrees. Oh, B's 5. Okay, 5 kilograms. So 5 times 40 is 200, which is 2 centimeters. 50 degrees north of east. So when I draw B after collision, let's at least get that one drawn. It's 50 centimeters, okay, 50 degrees north of east. And here's where I'm going to have a problem because I don't have the same scale you do. 2 centimeters. Cheat, don't look real quick. Don't look. Okay, so it's something like this. I can get it close, but I don't have my ruler's not going to work. It's not the same scale. But it's something like B pops off after collision, something like this, about like that. It's only 2 centimeters long. There goes B. That is little p b final. Now the question is, what you got to come up with is, using ghosts and all, is what is little p a final? They're not sticking together this time. So that's the question. What does that look like? What's the drawing look like? And then what's the description of that? So a strong suggestion is for you to have YouTube ready to go, and I'll give the links both in the the links are already on the sheet. If you go to where the sheets are on Facebook, the links are already there. But I'll add those links to the comments underneath this screenshots. Okay, so we'll do this today, tonight. We'll do a little bit more tomorrow on this, and then we're going to go to the component method, which is a bit of a nightmare. Talk about tedious. But I'm just going to do 1 or 2 of those, just to give you a feel for it. And then we'll get on to duck walking. We got to play glance ball in the hallway. That's probably be like a Thursday. We'll do that. Okay. Maybe we'll do it tomorrow. I don't know. All right, guys. Stop the sharing here. And any questions before I stop the recording? Okay, pause recording.